human batteries? Do we like charge ourselves up and then we can radiate that heat out for another couple of days? Hi, I'm Ryan. I'm a science teacher.
I'm Cheryl, and I slept through science.
Each episode will tackle a science question you may have learned in school, but can't quite remember or fully explain.
And I'll take the risk of asking the dumb questions so that we can all understand the science we slept through.
The bell has rung. Let's get started. Welcome to lesson 73. We are in our Invisible Things unit, and Cheryl, I'm guessing you have another question about something invisible.
I do, Ryan. Wow, that was like really good guessing on your part. I'm impressed.
Thank you.
Yeah.
That's why I'm the teacher.
Well, it's that time of year where it's warming up. And so recently I took my stepson to the pool. We had some fun pool time. It was great. And although I put on sunscreen, I still did get a bit of a burn, which, it's kind of like that first exposure to the sun during the summer. I feel like that tends to happen a little bit more. So that got me thinking, how do sunburns even happen, Ryan?
Oh, how do sunburns even happen? Okay, that's a great question. Let's start with the pre-assessment and find out, what do you think a sunburn even is in the first place?
Well, it's a burn on our skin.
Okay.
And now I'm realizing I don't know if I know how to define what a burn is.
Okay.
Much less a sunburn. But I mean, like, burns are like an exposure to heat.
Okay.
But I think the burns that were like make the most sense are where you like place your hand on the stove or, something like that, where like your skin is actually touching the hot thing.
Okay.
But then I know a little bit about sunlight because of our color unit.
All right.
So I know that there's these different wavelengths or like that are different things. And you talked about that beyond the color ones, there's all sorts of other ones like radio waves and something red, not ultra. There is an ultraviolet, and then red something or other. Red's the second word, I think. And so I think one of those is like the UVA, UVB light that we get sunburns from.
Okay.
But why is light actually burning our skin?
Okay. What do you think the light might be able to do?
Well, I know that it's energy.
Okay.
And so an energy produces heat. We've talked about this so many times. Is it produces? Is it something else contains? I think it produces heat, which is why the sun's warm in the first place.
Because
I don't know if that's
why?
why the sun is warm, but like that's why we can experience heat from sunlight. I don't know if that's why, but we can experience heat from sunlight. So some of that heat then can burn us too.
Okay, so maybe the heat is what's burning us?
Maybe. I mean, like the sun gets things hot.
Okay.
But it's not an object we're touching, it's just light. And it burns us.
Okay. What do you think is different about the light from the sun that burns us versus like the light in a room?
Ooh. Yeah, that's a really good question. Because the light bulb can get hot too. So there is heat also that can be produced from the light in our room. Not to the same extent, though. Is it just because it's that much stronger, or is it a different wavelength that our bulbs don't produce?
When you say stronger, what do you mean by stronger?
There's just more of the sunlight. Like the sunlight, the heat from the sun is strong enough that like you touch the patio and it's really hot, or different things like that. And if you have a light in a room on all day, it's not like things in your room are like hot to the touch because of the light. So it seems like there's just a lot more of it.
More of the light itself
from the sun. Yeah.
Okay.
But I think maybe it's a different wavelength because light bulbs are still pretty good at lighting up a whole space.
So what would, if it was a different wavelength, why would that make a difference, do you think?
I don't know, because I don't understand, like, why are radio waves able to be radio in a special way? Or like, why do these different wavelengths have different properties when all it is different speeds?
Different speeds, what do you mean?
Sizes of waves.
Sizes. Okay.
Yes. Okay. Like, why does that make enough of a difference that it could do totally different things?
Okay. I think that's a great question. In order to start the explanation, Cheryl, I think I need to start by just talking about what a burn is, which is where we started with our pre-assessment. And burns can be caused by lots of different things, as you talked about, but usually burns are caused when we touch something. And the heat energy from whatever that thing that we touch is flowing into our hand or whatever is touching it. And so it's actually gaining a lot of energy really, really fast. And the short version is it kills cells. And there's a bunch of different ways that it can do that. But one thing that can happen, and this is if it's a really bad burn, you can actually have the water that's in the cells actually vaporize if it's enough heat. Now, again, this is a really bad burn. This is not what's happening all the time. But you can cause that water to heat up because cells are mostly water. And then that can cause the cells to burst. That can cause them to die and then have their stuff leak out. It can cause all sorts of problems.
Oh, interesting.
Yeah. That's not exactly what's happening with a sunburn, but it's the same thing where cells are damaged and it's a problem. So that's true no matter what is causing the burn. Same thing with the sunburn. You knew light was involved, hence, sunburn.
Yep.
And you were trying to remember some of the different wavelengths of light, or the colors, quote unquote, that we can't necessarily see with our eyes. And you remembered radio waves, and you remembered ultraviolet, and something red. Did you remember what it was?
No. Oh, it's like there's cameras that pick it. Infrared.
Infrared. You got it. Nice job. Yeah. And we've even talked about before that what we generally sense as heat is in the infrared part of the spectrum. When you put your hand next to a campfire, but don't actually touch it, but you can feel the heat, that's infrared light. We just can't see it with our eyes, but our bodies can detect it. We feel that as heat.
Okay.
Well, then what does that have to do with ultraviolet light? Well, the key piece, and I think this is getting at one of your questions earlier, which was, why do the different wavelengths have different properties? You remembered that they did, but why is a radio wave different from an infrared wave, which is different from visible light, which is different from ultraviolet, and all of those things? It comes down to energy. And I think we may have talked about this before, but it definitely doesn't hurt to mention again. If you have a long wavelength, and I'm kind of using my hands to kind of make a wave up and down, but that is relatively wide and spread out. Okay, so a long wavelength, that energy in that light wave is spread out because the wave is relatively long. But as you start shrinking that wave, the energy becomes more and more concentrated. Does that sort of make sense?
Yeah.
And again, this is an analogy. This isn't quite how it works. But as I'm moving my hand to make it more and more shorter wavelengths, right? So it's more frequently that my hand is going up and down. My hand has to move more, right? Which requires more energy from me to do that. Eventually, it's not looking like a wave anymore. Just looking like I'm moving my hand up and down, and I look kind of ridiculous. Right? But so that's the short version is the amount of energy or the concentration of that wave that changes. As you decrease the wavelength, you increase the energy of the wave. So a radio wave is really, really long, doesn't have a lot of energy. Whereas ultraviolet light, UV radiation, which has more energy than the visible part of the spectrum. The ultra is a prefix that means more than or greater than. So ultraviolet is beyond or greater than the violet part of the spectrum, the purple part that we can see, think of like a rainbow. So it's beyond that, but it's beyond that at a higher energy. Visible light, which is mostly what comes from a light bulb, isn't in that ultraviolet. So while it can put out a lot of visible light that we can see, it's not really putting out anything in the ultraviolet. Old bulbs, the incandescent bulbs that used to get really hot that you talked about, the reason they were really inefficient, and remember we talked about light bulbs when we did, I think it was on Christmas lights.
Oh,
right?
yeah.
Right? And the LEDs are way more efficient because so much of the light that they produce is in the visible part of the spectrum. Old school incandescent bulbs, most of the light that they produced was actually not visible. It was infrared, which again, I said we feel as
heat.
Exactly, which is why they gave off a lot of heat, because that was also light, just light that we couldn't see, so it wasn't very useful. Well, as you move in the other direction, our light bulbs aren't putting off ultraviolet, and that's on purpose, because ultraviolet light can burn us because it's a high enough energy that it can actually cause damage to our skin cells. The sun is actually giving off all sorts of light in all sorts of wavelengths, but not all of it makes it to the surface of the earth because our atmosphere absorbs some of those wavelengths.
Okay.
You talked about UVA and UVB, and there's actually even a UVC, which are just different parts of the ultraviolet. Think of it like visible light, but we have red and green and blue and purple, right? So they're just different parts of that. And same thing for UVA, UVB, and UVC. UVC is the highest energy. UVB is in the middle and UVA is the lowest energy of the ultraviolet. UVC gets completely filtered out by our atmosphere. We don't really need to worry about it. UVA and some UVB does make it to the surface of the earth, and that's what causes sunburns. What happens is you can't see it because our eyes aren't sensitive to it, but included in the visible light is also the ultraviolet light. And if it gets on your skin enough, it starts to cause damage because it's higher energy that our cells can't actually absorb. They can't absorb all that energy without breaking molecules and sending electrons off and actually having things, because it absorbs that energy. When you feel warm, it's because your skin is absorbing that energy from the sun. Well, if it absorbs a high enough amount of energy, it can't contain that energy and it starts breaking things, but on like a molecular cellular level. And what actually the red part, the actual burn that we experience, is actually our immune system's response to the damage of the cells. Yeah.
Interesting.
So, and I'm not going to go into all of the details, but there's a great source that I'll link in the description that has a lot more description of sort of what's going on there. But it's actually an immune response that leads to the warmth. Think of like when you feel super warm on your skin, that's usually because your body has increased blood flow to that area.
Oh, okay.
And so the more blood, which has the internal body heat, right? That's why oftentimes, like when you're really hot, like you get flushed, right? You get kind of a red color if you've got a lighter skin tone, because more blood is rushing to the surface of your skin so that it can radiate that heat out and you can cool off like the core of your body. Okay. So it's a similar sort of a thing, except now it's not to radiate out the heat. It's because they need more blood, because blood has all the different types of things that can help heal damaged cells.
Interesting.
So that's where a lot of that red comes from. And that's where that heat comes from, is the heat from the inner part of your body that's radiating off. It's not actually heat still from the sun, which if you think about it, sort of makes sense. Like why would it? Because you often also don't feel the burn right away. It's like a delay.
Yeah.
Which if it was from the sun, it'd be like, oh, are we human batteries? Do we like charge ourselves up and then we can radiate that heat out for another couple of days? It's not really like that.
Interesting.
And now, Cheryl, it's time for your quiz.
Well, I am actually, I already did my quiz because I already got the sunburn and experienced the heat from the sun and from my body and all the things. So we're good.
So are you saying you're already enlightened?
Oh, boy.
Sorry, still got to do the quiz. All right, first question. Name 3 different wavelengths of light.
Oh my gosh, I forgot the red one again. Infrared.
Okay.
Ultraviolet. Radio wave.
Yep. Those all work.
And the rainbow.
That's visible light. Yep.
Okay, fine.
Look at that. You got a bonus one for 4. Okay. What is the main difference between the different wavelengths of light?
I was about to say the lengths of the waves, which you did call them wavelengths. So I don't know if that exactly counts. Some of them are moving faster than others because the waves are shorter. I'm just going to do this because this was part of your lesson.
With your hand moving your hand again?
Across the screen like a wave.
But why did I move my hand like that? What was that supposed to show?
Because some of the waves have longer distances, or longer waves, and they're slower.
Yeah.
And then some of them are much faster and have more energy.
Means, there you go. They have more energy. There we go. That's what we were looking for. Okay. Why can sunlight burn us, but light from bulbs doesn't?
Because there's no UV in bulbs.
That's right. I mean, unless you get a UV bulb, which I generally don't recommend.
Yeah.
But there are instances where you would want to. But for example, we have goggle cabinets at school where we can store the goggles, and they have UV bulbs in them because it disinfects. Cool. And I don't know if you remember back in the COVID times, one of the things, they had the little robot sometimes that would go through with ultraviolet light because it would destroy and break down viruses and also bacteria in the same way that it can break down the cells that we have. So, yeah. What happens to our skin cells when we have too much ultraviolet light?
They die.
Any more detail?
Yeah, let's see. I'm trying to think of how to describe it now. I feel like you described a lot of things happening.
I did.
To the cells, something about molecules and that our little bodies try to save us by having our immune response come to the rescue, but then it just makes us all red and warm. So that's dramatic.
It does, which that was the next question, was what causes our skin to be red?
Oh, there we go.
Yeah. But the other piece with the skin cells is it starts to break apart molecules.
Okay.
Right? And it can kind of cause damage. It can kill the cells, but it can also just cause damage too. It doesn't always kill them immediately. The ones that are dead, that's actually why over time you end up with the flaky. Those are the that's because those are all the dead skin cells that eventually work their way up to the top, and they're dead. Get rid of them. Let them go away. So there you go, Cheryl. You know everything you ever wanted to know about sunburns now.
Amazing.
And I don't feel like it would be a complete lesson about sunburns if I didn't remind people to wear sunscreen, because not only can you get a sunburn, but that damage can also happen to DNA. And that's what can lead to skin cancer, is because the ultraviolet can also damage, because DNA is a molecule, just like anything else. And so if you have that damage repeatedly over long periods of time, it can add up, and that's what can lead to skin cancer. So make sure that you are protecting yourself with good old sunscreen.
Yepers.
All right, I think that's all the time that we have for today's lesson. So why don't you pack up your stuff and get ready for my closing remarks. You can follow us on Instagram and Facebook at I Slept Through Science, or on Twitter at Slept Science.
If you have dumb science questions like I do, please send them to us. You can email us at isleptthroughscience@gmail.com, or you can even send us a voice memo and we'll play it on the podcast.
Please rate and review our podcast to tell other people what you think about it, subscribe to make sure you don't miss an episode, and share about our podcast on social media.
Thank you to Beth Reed Miller for the artwork. You can check out more of Beth's artwork at Beth Is Something. Okay, great. Thanks. Bye.
The bell doesn't dismiss you. I dismiss you.